Okay, we've been talking about integrals and how we can use them to calculate area under the curve. And we know that when we calculate area, we have the ones above the x-axis is positive and the part below the x-axis is negative. So if we just take an integral of this function from let's say 0 to 5, we'll call this f of x, then we're going to end up with a net area because this area is negative, this area is positive, and if we just do the integral from 0 to 5, we end up with just the net. Now, we can also figure out the total area, though, and we talked about this as well. So if we split it up, let's say this is at 2. If we split it up and we said the integral from 0 to 2 of the function, and then subtract, so that we'll change the sign, of the integral from 2 to 5, then this would give us our total area. So we have this subtraction sign here. We'll change the sign of this part so that we add it all up. Now the other way that we could do this, which we also briefly discussed, is we could say the integral from 0 to 5 of the absolute value of f of x, and that would also give us the total area, because then the absolute value of f of x would pull this part up here, and it would be positive area. So the thing you need to remember is your integral is a net change, not a total change. Now, hopefully you have your notes sheet that I handed out in class that says 7.1 integral is net change at the top of it, and we're gonna go through this note sheet and work on some of these examples so you can have this. Now, one way to help us look at this is if you say 2 steps forward and 1 step back. Well, 1 step forward, 2 steps forward, and then 1 step back. Well, in total, you've traveled 3 steps, but your displacement, which is net change, is only 1 step, because you're really only, if you start out here, you take 2 steps forward and then 1 step back, you end up only 1 step away. That's your displacement. Okay? To find the displacement, you just have to find the integral. Now remember, we talked about if we had a constant velocity of 50 miles per hour and we traveled that for 5 hours, then this area underneath the curve would be our total distance traveled. Remember that this is the velocity function and this is time. Then the area under the curve is what gives us our displacement. So when you have velocity, if you take the integral from a to b of the velocity function, then you're going to get your displacement, or your net change in how far you went from the beginning. Now, if you want to find the total distance, then you're going to have to find the integral of the absolute value. Now, this is all in the box at the top of that note page, so make sure you're looking through that. So you have to remember the integral of velocity is what gives you how much you've traveled, because remember, an integral is an accumulation of the changes, so accumulation of how far you went in each little time period. So we add all those up and we get our total displacement. So let's look at that example 2 there. It says, suppose the velocity of a particle moving along the x-axis is given by this function, v of t equals 6t squared minus 18t plus 12. And we're only looking at the time from 0 to 2. So if we want to know when the particle is moving to the right, okay, moving to the right means our velocity is positive. Moving to the left means our velocity is negative. And then when it's stopped is when our velocity is equal to 0. So hopefully you remember that. So when we look at that, you can graph it. So let's see if we can actually get our graph to work here. Let's see. Alright, so if we put this in, we've got 6, we'll use x squared minus 18x plus 12. If you graph that, let's see. Sorry, it's not working very well, is it? There we go. If we graph this function, here's in a standard window, but really we only need to go from 0 to 2 because of our limited domain for this function. So we've got a graph like this, and we see here is a point where it changes sign. The velocity is positive up here, all the function values are positive here, and it's negative here, and it's 0 right here and right here. So what does that mean? Well, we can use our calculator to calculate the zeros. And hopefully you remember how to do that. And you get a 0 as x equals 1. So that means that we're moving to the right from time t equals 0 to t equals 1, and that we've stopped at t equals 1. Then we're going to the left from t equals 1 to, and then we have to find this other 0 here. Now, you could also, of course, find this, and it's going to freak out again. You could also, of course, find this using a using your factoring. If you factor it, then it will, you'll see that it factors out nicely. And it's not going to work. All right. So hopefully you can just get it to work on your calculator, and you won't have to worry about this. So if you graph it on your calculator, we've got this graph here. Looks like this. And you'll find this is the first 0 we found, that was 1, and this is the second 0. It's actually at 2, because we could have factored this 6 times t minus 3t plus 2, which is 6 times t minus 2 times t minus 1. And you would see that you have these zeros. So anyway, sorry, calculator snafu there. So we see that our velocity is positive when we're between 0 and 1, and our velocity is negative between 1 and 2, and it's 0 at 1 and 2. Now this, we're actually looking not at the area, we're looking at the actual velocity, so what the actual function values are. So then if we want to find the displacement, in part B it asks us to find the displacement. So remember, displacement is the net change. We know this area under the curve is going to be positive and this area over here is going to be negative, but we want to know the displacement. How far are we from the beginning? So what we need to do is take the integral from 0 to 2 of our velocity function. So our velocity function is 6t squared minus 18t plus 12. And we're going to take that integral with respect to time. So we just integrate this, did the antiderivative, so we have 2t cubed minus 9t squared plus 12t. And remember, since it's a definite integral, we don't have to worry about the plus c because it'll add and subtract off. We're going to evaluate this from 0 to 2, and when you calculate this out, you get 4. So we plug 2 in here and get it all out, and then subtract off. When we plug in 0, we just get 0. So we'll have 16 minus 36 plus 24. And that gives us 4, which means we moved 4 units to the right from our initial position. Because it's positive, so we know that that's to the right. So that's our displacement. Now, what if we want to find the total distance traveled? Now, in part C, it asks you to find the total distance traveled by setting up one integral and using your calculator. So you're going to have to do that on your own because since my calculator application thing isn't working. But you just go to Math and over to Num, and you can find that absolute value. And remember, if you do Math and it's number 9, the FN int, that's going to help you get to your integral. So you take the integral from 0 to 2 of the absolute value of this function. So when you do that, you'll plug it in your calculator and you should get 6. If you're having trouble getting that, you need to make sure you ask me because you need to know how to find these integrals on your calculator for sure. Alright, now part D asks us to find it without using absolute value. So what that means is we're going to split it up. Well, where does it split? It splits at 1. So we're going to go from 0 to 1 of our velocity function. And this is a positive area, so we're just going to leave it positive. And then we're going to subtract off, because this is a negative area, so minus a negative will make it positive, the area from 1 to 2 of our velocity function. So then we take our antiderivatives. We've already figured that out. We're going to evaluate it from 0 to 1 here, and then we're going to evaluate it from 1 to 2 here. And when you plug in all the values, so you'll plug in 1 and you'll get 2 minus 9 plus 12 minus, and then minus 0, so that'll go away, and then minus, we plug in 2 here and we get 4, which we already knew from up here, and then minus a negative, so that'll be plus, and then 2 minus 9 plus 12 equals 6. I kind of ran through that calculation, but hopefully at this point you guys can handle that. So our total distance that we moved was 6 units, but our final displacement, our net amount that we moved, was 4 units. Now, you can use your velocity to find displacement, but there's other things that you can do as well. If you look at the top of the next page, it talks about consumption. If you have a graph that tells you how many tickets per hour that you've sold, and then this is the time, and you want to know how many tickets you sold from time A to time B, this area underneath here will tell you the number of tickets sold. So anytime you have a rate of change with respect to time, and then you have the time, if you want to find out how much the total of that stuff happened, then you can take the integral and it'll give you that net change. Now, this next example, since the calculator is not working, is I'm going to talk you through it, but we may have to look at it in class because you really need to see it with the calculator. So example 3 says the tide removes sand from Sandy Point Beach at a rate modeled by the function given by r. So we have, this is the removal rate with respect to time. Okay, so we're removing volume. So it's cubic yards per hour is what they end up giving us. And the pumping station adds sand, so this is removing, so it's negative. And we're adding sand, this is positive, with this function. And again, both R and S have units of cubic yards per hour, and time we're going from 0 to 6 hours. And they give us an initial condition at t equals 0. We've got our initial value is 2,500 cubic yards. So that's where we start. And then the tide starts removing stuff with this function, and the pumping station is adding it with this. So how much sand will the tide remove from the beach during this 6-hour period? Indicate units of measure. Okay, so we want to find how many cubic yards the tide removed. So we want a total of how much has been removed from the beach. So we're just looking at this removal one here. Now, what's going to be easiest for you is if you take this and put this in as y1 in your calculator and put this one in as y2. And then you'll be able to do these on your calculator pretty easily. So what we want is an integral, because right here we've got this rate and we just want the amount. So when we take an integral, we're going to, that per hour is going to go away because we're doing it with dt. So we have the integral from 0 to 6 of this function r. So in your calculator you can put the integral from 0 to 6 of y1. Make sure you're in radian mode, please. dx is what you'll put it in your calculator, and you'll end up with 31.8159 cubic yards. So that's how much the tide has removed during the 6-hour period. Now, the second part asks you to write an expression y of t for the total number of cubic yards of sand on the beach at each time. So we want how much sand is there. Well, what did we start with? We started with 2,500, and then we have to figure out what we're removing and taking away, and adding. So what we need to know is the total amount, the net change of what happens with the removal and the adding it on. So we're going to start at time 0, and then we want a function of t. So we're going to leave this t variable up here, and then we're going to say, well, we're adding this amount, and we're subtracting off this amount. This is our net change in the amount of the function, and we're using our fundamental theorem of calculus to realize that when we do this we'll get antiderivatives, and it'll be a function of t when it's all said and done. So here's our function. Y of t is 2,500 plus the integral from 0 to t of s of x minus r of x. That way we end up with our function of how much is there, how much sand is there. This tells us how much total it's changing over the time period, and this is what we started with. So then part C says, find the rate at which the total amount of sand on the beach is changing at t equals 4. Well, this is our function of how much is there. So what's our rate of change going to be? That's right, the derivative. Y prime of t is the rate of change. So when we use y prime of t, we use our fundamental theorem of calculus to take the derivative of this function, and we get that y prime of t is just s at t minus r of t, because the derivative of 2,500 is 0, and then the derivative of this integral, using the fundamental theorem, is just s of t minus r of t. So on your calculator, you can plug this in. You say, if we want to find what happens at 4, you plug in y, that's y2. y2 at 4 minus y1 at 4. Do that on your home screen, and you'll get negative 1.9088 cubic yards per hour. So what this is telling us is at time t equals 4 hours, then the amount of sand is changing. This amount, it's going away at negative 1.9088 cubic yards per hour. It's going away. So then what we need to do is look at part D here. See if I have room for this. For the time from 0 to 6, at what time on the beach is the sand on the beach a minimum, and what is that minimum value? So we're looking at a closed interval. We want to know about minimums and maximums. So we're looking for our critical points. Our critical points, remember, are the endpoints, so 0 and 6. And then, so we want to check our critical points, which are at t equals 0 and t equals 6, and also when the derivative equals 0 or is undefined. So when we look at this, what the best thing to do is to make a graph and plug it in y3, and your y3 put y2 minus y1 because that's our derivative here. So if you look at your graph, make sure you unhighlight the y1 and the y2 so you're only looking at the y3. So what you need to do is look at those, and then you'll be able to see the critical points. And you'll get your 0. If you calculate the 0 with that on your window from 0 to 6, remember you're looking at time from 0 to 6. So you look at your window from 0 to 6, take this graph and find the 0 there, and you'll get your 0 at t equals, will be x on your calculator, 5.1178653. Okay, if you go back to your home screen, you can just type x and then hit enter, and you'll get this value. And then store that as something. A is what I used. I just used the alpha key, and that way you have all the decimals, because it's much better if you can deal with all the decimals. So then on your calculator, what you'll have to do is, you know that this is the time that we're looking for, but if we want to know what the actual amount is, that means we need to take this time and plug it into this function here. So on your calculator, what you can do is type 2500 plus the integral from 0 to a of y3 dx. You type that in. If you've stored your x value as a, this x value here, and then you'll get that you have 2,492.369 cubic yards of sand at that particular time. So that's the minimum amount, right? We want the amount of sand on the beaches at a minimum. That's the minimum amount. So we found a minimum for this function, which means we used the derivative to find those critical points. If you look at the values at 0, it's 2,500, of course, and then at t equals 6, you calculate that out, and it's 2,493.2766. So it's just a little bit more. So we reach our minimum right before the end of this time. Hopefully that made sense. Go back over it, pause it, play with your calculator, make sure you've got this all, because you definitely need to be able to do these things in your calculator. If we need to go over this one in class, since the calculator wasn't working for this, then we will.